All right, good morning, everybody. Let's do a little refresher of what we talked about on Tuesday. So we started talking about this idea, right, of electrophilic aromatic substitution, being able to react aromatic molecules with certain reagents and getting new molecules out of that reaction. So I've drawn three such things on the board. I want you to get in your pairs and take a few minutes and try to figure out what reagent we need, what needs to go over the arrows to do those reactions. Okay, so take about a minute each, try to figure those out, and then we'll go over them together. All right, folks, let's go over these three. This first reaction is an electrophilic aromatic substitution. We're replacing the hydrogen, or one of the hydrogens, on the benzene ring with a bromine. What reagents do I need to make that work? I need Br2, but if I take just Br2, nothing happens, right? So I need something else. And I need FeBr3. That's right. And so that mixture makes Br plus, right? And so that makes the electrophile, or the bromine, electrophilic, right? And so we know that that's going to do that. The second reaction, right? We're replacing the hydrogen on the aromatic ring with an NO2 group, or a nitro group. We call this nitration. What reagents do I need to affect this reaction? HNO3, and what else? H2SO4. So I need a mixture of nitric and sulfuric acid. And, you know, typically it's 1-to-1 by volume, usually when people do this reaction. But other concoctions are available, or ratios, if you will. This reaction down here, we're replacing the hydrogen with what's ultimately going to become a ketone. You know, this is called an acyl group, right? First off, before we think about the reagents, what's the name of this reaction? This was one that has a name. Okay, this is Friedel-Crafts. Is it alkylation? Acylation, that's right. We're not putting an alkyl group on there, we're putting an acyl group, right? So this is the acyl group, the carbonyl, right? So what do I need for this? I need aluminum trichloride. And I need something else. I need something that's got some carbon, right? What's that something that I need for carbon, for the carbons? What was the functional group that I told you about? We said we reacted with aluminum trichloride. Pardon?
C2Cl.
Close. So I need CH3, C double bond O, and then Cl, right? So I've got to have CH3, C double bond O, Cl. And these are called acid chlorides, right? So the chlorine here is going to react with the aluminum trichloride and give me the carbocation there that will do the acylation. Okay? So that's how that works. Okay? You need to have these reagents memorized. You don't want to be in the middle of an exam and have to look these up. You know, I know that if I'm going to put a bromine on an aromatic ring, I'm going to need something like this. What other halogens can I use? I can use chlorine. In that case, it would be Cl2 and FeCl3. Can I do iodine? No. Can I do fluorine? No. Not in this reaction anyway. Okay. Nitric acid for and sulfuric acid for the nitration, and acid chlorides and aluminum trichloride for the Friedel-Crafts acylation reaction. Okay. So we talked about others, but just wanted to give you a quick little review on a few, and so we've done that. So let's suppose we've got a benzene that already has a group on it, and we want to do a reaction, right? So let's just focus on something that is already on the board or on the screen, and that's aniline. Aniline, of course, the nitrogen has a pair of electrons. And so if you're an electrophile and you're going to react with the aromatic ring of aniline, you would think that you have three possible choices. You could react here, here, or here, right? Here happens to be the same as there happens to be the same as there, so they're equivalent, right? So you really have three choices where the electrophile can go. And so you might expect to get a mixture of all three. But when you do the experiment, you find that you don't get all three. And in fact, you only get a couple. And the reason has to do with the fact that the amount of electrons, okay, or the electron density as we like to call it, is not the same with all three carbons. Okay, it just isn't. Why isn't it? It is not, because we can draw resonance structures for aniline, and that's what we have on the screen. Right? So if you look at the lone pair of electrons on nitrogen, we can draw a resonance structure that pushes those electrons into the ring and pushes electrons onto the ortho carbon. Remember, we've got ortho, meta, and para for an aromatic ring. So I've got a lone pair now in this resonance structure that puts electrons and a negative charge on the carbon right next to the aniline group. I can draw another resonance structure that pushes those electrons onto the 4 position, which we would call the para position, and I can draw another resonance structure which pushes those electrons on the other ortho position, and then of course we can get back to our starting aniline. So if you're an electrophile, where would you want to react? Ortho, meta, or para? Wherever the electrons are at. And where are they? They're ortho and they're para, but they're never where? They're never at the meta position. So electrophiles will react with substituted benzenes that at least have a lone pair of electrons on them, such that you get things only happening at the ortho and pair of positions. So let's look at a different example. Let's say you take phenol. Which has an OH. And oxygen we know has two lone pairs on it as well to keep the octet. And let's suppose that Baron takes that and reacts it with bromine and iron tribromide. What products would you predict that we would get? What do you think? Where would the electrophile go? You want electrons, right? You're an electrophile. Well, when we looked at aniline, where were the electrons? They were on the nitrogen, but they got pushed into the ring by resonance, right? So where on the ring are the electrons through the resonance structures? They're ortho and para. So you would anticipate that you would get a mixture of this and this. Okay? Now, if you were in my 255 or 256 organic class, we go into a lot more depth and try to figure out which one's going to be the major product, which one's going to be the minor product. That's not important for you all. Okay? What's important is that you recognize that not all of these carbons are equal in terms of their reactivity because of how we draw resonance structures, just like we did for aniline. Right? I can do that as well for phenol. And I'm just showing one resonance structure, right? But you could draw the others as well. You all can do that. And you would predict that you would get a mixture of the ortho and the para-substituted phenol. Okay? When we have a group attached to an aromatic ring where the atom that is directly attached to that aromatic ring has a lone pair of electrons, we say that that benzene ring, or that aromatic ring, is activated. It wants to react. It's got more electrons in it than you might anticipate because of resonance. Okay? And so it's an activated ring. And activated rings will give you ortho and para substituted products. Now, if I have an activated ring, I can also have a deactivated ring. We'll talk about that as well. So here's an example of a deactivated ring. So let me just draw this up here. Right? So they're talking about, what's that functional group other than the aromatic ring? What's this functional group right here? Look at the name under the molecule on the screen. What do you think? It's an aldehyde. So this is an aldehyde. So this atom, this carbon atom that is directly attached to the aromatic ring, does it have a lone pair of electrons? No, it does not. So do you anticipate that this is going to be an activated or a deactivated ring? It is a deactivated ring. And in fact, what we can do is we can draw a resonance structure that pushes the electrons onto oxygen, and then that pulls electrons out of the aromatic ring by resonance. Where are we pulling the electrons out? What positions are losing the electrons? In other words, where are the positive charges? Ortho, meta, or para? Ortho, that's one. Where's the other one that has the positive charge? Para. Where does it have a positive charge? Meta. So if you're an electrophile, you're positively charged, right? Are you going to want to go to the places that are positively charged or the places that have no charge? What do we know about like charges? Do they attract or do they repel? They repel. So if you're positively charged, you're not going to want to go to the ortho positions or the para position because there's some charge there, at least formally, right, when we draw the resonance structures. You're an electrophile. You're going to want to go where the electrons are. And positive charge, by definition, is minus electrons, right? Absence of electron. So if I was to take this molecule and react it with bromine and iron tribromide, what product do you think I would get? You see? I don't need to give it away. What do you think we'd get? Would we get orthobromobenzaldehyde? Would we get metabromobenzaldehyde? Or would we get parabromobenzaldehyde? We would get meta. Yeah, we would only see, for the most part anyway. I drew it like that, so let me draw it like that again. Right? That's 1, 2, 3. That's 1, 3. That's meta. That's what we would end up with. These are called deactivated rings because we're pulling electrons by resonance out of the ring. Which one of these rings do you suspect would react the fastest? Benzaldehyde with the bromine or phenol with the bromine? Phenol. Activated rings react faster. They also react such that they give ortho and para substituted products. Whereas deactivated rings, they react slower, but they give meta products. Okay? So you have to look at the group that is attached to the aromatic ring and determine whether or not it's an activator or a deactivator. For your purposes in this class, look at the atom that's attached to the aromatic ring. If it has lone pairs of electrons, it's an activator. If it does not have lone pairs of electrons, it's a deactivator. Now, alkyl groups, just like a CH3 or something like that, they also fall under the activator list. Okay? Even though they don't have lone pairs of electrons. Okay? So, let's look at some examples. If I start with bromobenzene, is that an activator or a deactivator? Remember, we chemists don't always draw the lone pairs of electrons, do we? Does bromine have other lone pairs of electrons? Yes. Right? So I would predict, based on what I just told you, that that's going to give me ortho and para products. Okay? If it was to react with some other electrophile. Okay? What about if you started with nitrobenzene? Nitrogen is attached directly to the ring. Is that going to be an activator or a deactivator? You might think it's going to be an activator because of what we did with aniline, right? That nitrogen had a lone pair of electrons. This is where you have to pay attention to Lewis structures. If I was to draw the Lewis structure out for this, it would look like this. That's the Lewis structure for the nitro group. And it's positively charged. And it doesn't have a lone pair of electrons on it. So now what would you say it is? It's a deactivator, so it's a meta director. Okay? Here's an example of where we're dealing with methylbenzene, also known as toluene. I told you that alkyl groups are activators, And if you were to go into the lab and take a little bit of toluene and react it with bromine and iron tribromide, you would find that you get really two products. You get about 40% of the orthobromotoluene, and you get about 60% of the para-bromotoluene. And they say trace, but in reality, if you were to go up in my lab and do this right now, you wouldn't be able to detect the meta product at all. Okay? You just wouldn't. It's, 60 plus 40 is 100. So that's really what you're going to see. You're going to see those two products. Can you take a guess as to why that's not 1-to-1? Why isn't it 50-50?
The size of the substituents.
Yeah, the size of the substituent. What do we know about bromine? Is it small or pretty big? It's pretty big because it's down far on the periodic table. And we know as we go down a family, it gets bigger. What do we know about a methyl group, a CH3, relative to a hydrogen atom? Big or small? Much bigger, right? So I'm trying to get two big things close together. Does that seem like that should happen? No. But what happens in the para? I've got the two big things as far apart as I can get them, right? And so what we see is we see a little bit more of the para product over the ortho product, okay? Molecules are just like people. They don't like to be crowded. Nobody likes to be crowded, right? So same kind of thing here. So the alkyl group, you can clearly see this is an ortho-para director, so I know it has to be an activated ring, right? That CH3, even though it does not have a lone pair of electrons on it, functions in a way to activate the ring through what's called hyperconjugation, and we're not going to get into that, okay? So if you have an alkyl substituted benzene ring, you need to know that it's going to give you ortho-para products. If you have a nitro substituted benzene ring, you need to know it's going to give you meta products. If you have a halogen substituted ring, you need to know it's going to give you ortho and para products. Okay? If I have a carbonyl attached to the aromatic ring, either an aldehyde or a ketone, that's going to give me ortho para meta. Meta, that's right. So if I have something like this, right, that's going to give me meta products. Okay? Good. Now, if you look at taking something like nitrobenzene, we just said that the nitro group is a meta director, right? Deactivates. We can actually take nitrobenzene and we can heat it up a little bit with some nitric acid and sulfuric acid, and we can try to put on another nitro group. And what you'll find is almost all of it gives you the meta-dinitrobenzene. Get a little bit of the ortho, but that's pretty small, minor stuff. Okay, we don't need to worry about that. The major product here is the meta product. So, you come into the lab, it's World War II, you're trying to win the war, right? We have a big vat of toluene. You put a lot of nitric acid in it, and a lot of sulfuric acid. I mean, it's there in excess. What do you think the product's going to be? Assuming you don't blow yourself up. TNT, I heard somebody say it. What's that stand for? Trinitrotoluene. So we're going to put on 3 nitro groups. So I've got my CH3 here. CH3, is that an ortho, para, or meta director? It's an activator, right? So it's going to be ortho para, right? Okay? So I'm going to put a nitro group there. But I've got a lot more nitric acid and sulfuric acid. Where will the next one go? I've got something that directs ortho and para, and I've also got something now that directs, what does this one direct? Meta, right? Where's meta to this? Meta to this is here and here. So where does the next one go? Notice that meta to this is also para to that. So it goes here. That's all right. Where does the third one go? What's meta to this one? That. What's meta to that? That. What's ortho and para to that? That and that, right? So where's it go? It goes right there. The third one will go right there. That is trinitrotoluene. This is how they make TNT. The first one goes on real easy. Real easy. Second one's not too terribly hard. The third one, you got to heat this up for it to work. Do you want to heat an explosive? Probably not. So there was a lot of engineering that goes into making TNT to make sure that you don't blow up your plant, right? And so you end up with trinitrotoluene, one of the more powerful traditional explosives that we know of. In fact, anything with a nitro group on it can technically be considered an explosive. But it's just sophomore level organic chemistry that makes it. You all could work the mechanism out for this. You all could go into the lab. You've got the glassware. We've got the chemicals on site to do this. So what keeps people from doing it? Putting that third one on, chances are it'll kill them. It'll usually go boom. And using just regular laboratory glassware, right? This is why rarely do you hear of terrorist attacks where they have used TNT as the explosive. They typically use other things that are less hazardous to make.
So since you added 3 nitrogen groups, would you have to have 3 of the?
Yes, you have to have a lot of this. I didn't draw the stoichiometry, but yes, you would have to have a lot of nitric and sulfuric acid. In fact, they use more than 3. You have to get that third one on, it's hard, so you have to really add a lot of reagent. It's not easy to do. And other than the fact that it explodes, these nitro groups deactivate the ring, and so it gets slower and slower every time you add a nitro group to make it work. Okay. So, the last piece that we need to talk about out of chapter 9 is phenols. And phenols are a special group. They're a special kind of alcohol. And so for those of you who read ahead, what is so special about a phenol? It's an aromatic ring, it's a benzene ring, but it just has an OH on it, right? But we say that this is a separate functional group. We don't call it an alcohol, even though it looks like an alcohol, right? What's special about it?
It's very acidic.
It is unusually acidic. Yes, right? Why is it unusually acidic? It is unusually acidic because if I lose the proton, the conjugate base, that's highly stable. Why is that highly stable? I can draw resonance structures for it. Okay? Most alcohols have a pKa of above 16. Ethanol has a pKa of around 16. Methanol has a pKa of about 15.7. Butanol has a pKa of around 18 or 19, if I remember my numbers right. Phenol has a pKa of just below 10. And remember, the lower the pKa value, the greater the what? The acidity. I can deprotonate phenol with sodium hydroxide. Okay, just good old Drano drain cleaner will deprotonate phenol. Okay, and so the phenol functional group turns out to be pretty important because we can do a lot of stuff with it. You all depend, believe it or not, on the phenol functional group. Let's see if I can remember the structure. And then there's a methyl group and an R group here. We're not going to worry about what the rest of it is. This is the structure of vitamin E, more or less. The R group, I don't remember all the carbons that are in the R group, or how to draw them out. But there's an R group there, okay? What is so important about vitamin E? I know I've got some nutrition majors in here, right? What's so important about vitamin E? Why is it important? Do I need vitamin E? The fact that we call it a vitamin seems to suggest that we need it, right? Why do we need vitamin E? What does vitamin E do for me? Can I get sick if I don't have enough vitamin E? I can. I can get quite ill actually if I don't have a sufficient amount of vitamin E. So why do I need it? Vitamin E, for lack of a better term, keeps you from rotting. Keeps you from going rancid. Right? We have lipids, we have fatty acids, our cell membranes are made up of these things. They oxidize in air. It's like olive oil, will go bad after a while and it gets that yucky, filmy stuff. The same thing would happen to you if you didn't have things like vitamin E in your system. Vitamin E is an antioxidant. Phenols are good antioxidants. Okay? They keep you from going rancid. Okay? So, it turns out that vitamin E gets into these particles called low density and high density lipoprotein, HDL, good cholesterol, LDL, bad cholesterol. And the vitamin E keeps those particles from oxidizing because it's when they oxidize that they make plaques. Where do the plaques form and cause problems?
Your veins.
In your veins, in your arteries, your heart, right? People have, I'm like everybody else. I like a good fatty diet, right? Sausage is good and all that kind of stuff. I like it. But eating all those lipids, right, puts a lot of HDL and LDL in our bloodstream. And if those things get oxidized, they will plaque out and cause atherosclerosis, okay, which is the clogging of the arteries or the hardening of the arteries, okay? Vitamin E is a very potent antioxidant. It's a naturally occurring antioxidant. And there are other synthetic versions that are also available, okay? But that's what phenols are good for the purposes of this class, okay? They're very good. What would happen, you think, if we took phenol and we reacted that with an excess, that's a key, of nitric acid and sulfuric acid. Take a moment and figure out what you think the structure would be. Let me give you a hint. You need at least 3 equivalents of nitric acid. So you've got phenol, you've got a lot of nitric acid, sulfuric acid, you stir it around, you mix it up. What do you think will happen? Help me draw out the structure. What do you think we're going to get? What do I need to draw where? What do you think, Rose?
I think you need 3 equivalents of the nitrogen.
Okay, so we're going to put 3 nitro groups somewhere, right? Where are we going to put them?
The same orientation as the TNT.
Okay, which is what?
Okay, left, right, bottom.
Left, right, and bottom. Okay. Ortho and para, right? And in fact, this is what you get. What do you think about that molecule? Pardon? Looks a lot like TNT, so what might you expect?
It's
you might expect that it's explosive, yeah. This is a molecule, I don't know if I still have any up in my lab or not. It's called picric acid. Picric acid. And as long as it's wet, then you can use it. I'd give it to you all to use. No big deal. But if it's dry, just turning the cap on the bottle can make it go off. Boom. Why do you think we call it picric acid?
It's picky.
Because it's picky. Okay. Well, okay, kind of. It does kind of look like pickle juice, oddly enough. I don't know if that's where it came from or not. It kind of has a yellow tint, kind of like old pickle juice. Okay? I don't know if that's where the name came from or not, though. That's a good guess. What about the acid part? What do you think this molecule, it's an acid. This is a pretty strong acid, actually. Not only is it explosive, it's a pretty strong acid. And in fact, it likes to exist in its deprotonated form. When you put it in water, it's really more like this than like this. And it turns out that this is a highly colored molecule. Okay. Now you might be wondering, why in the world would a chemist like me have picric acid around? Well, it turns out that it's useful for a number of reasons. One, it helps us sometimes grow crystals, if we're trying to grow a crystal of a molecule so that we can get an X-ray structure of it or whatever. Picrates are good for that. But also some of my friends, when I was at the University of Oklahoma doing my graduate work, there were colleagues, not real close friends, but colleagues that were in the biology department who studied birds. And they would come up to our lab and get a little bit of the picric acid in water. And when they would catch birds, they would dip it into the picric acid and they would write on their feathers, whatever it is that they were writing on it. It turns out that this is fluorescent, so you can shine a UV light on it and you can see it. And somehow, I don't know how, but it gets incorporated into the feather and it becomes waterproof. So they could actually label the birds and then release them again. So here's these little explosive birds flying around. No, they're not really explosive. It's very little material. But it would get into the feathers. It wouldn't harm the bird. It would allow them to, without having to put a tag, they could then release them again and recatch them and then figure out which bird it was. So that was always kind of fun. But we always did make the joke that there were explosive birds flying around the University of Oklahoma. And so they would come and get a little bit of it from time to time to do that kind of stuff. All right. Let's jump into chapter 10. We are not going to get done with the material today, and that's okay. We'll pick it back up next week on Tuesday. And as you can imagine, when I regularly teach the class, this is about, when I teach it in the fall, this is usually around Thanksgiving time, given my little cartoons there. So we're going to talk about amines in chapter 10. Okay? Talk a little bit about nomenclature, not a lot. You all can figure that out now. We'll talk a little bit about some interesting amines, how they're made, how they function. So that's what we're going to try to get out of chapter 10. It turns out that the amine functional group is going to be one of the more important functional groups for those of you going on to biochem. The reason is the amine functional group is used to make proteins and peptides, muscles, right? You take amino acids and you put them together and you make biomolecules. So how the amine functional group works is going to be very, very important for you, okay? You all might recall, this is a little review, we can have primary, secondary, and tertiary amines. Remember, a primary amine is where the nitrogen is only attached to one other carbon. A secondary amine has the nitrogen attached to 2 carbons, and a tertiary amine has the nitrogen attached to 3 carbons. What is common among primary, secondary, and tertiary amines? The lone pair. All amines must have a lone pair of electrons on the nitrogen. Can I put a 4th group on the nitrogen? Yes, I can, but it is no longer an amine. It then becomes an ammonium salt. Okay? An amine must have a lone pair of electrons on the nitrogen. Okay? So I can have primary, secondary, and tertiary amines. The R groups can be the same or they can be different. It doesn't matter. Okay, so if I have what kind of amine is that? That is a secondary amine. I have a carbon here and I have a carbon there, right? That is a secondary amine. It's a primary amine. Anybody in here Breaking Bad fans? Anybody ever watch Breaking Bad? Yeah, a few people? Yeah, I watched it many times. It's pretty cool, right? Remember when they were, for those of you who watched it, when they were robbing the train car full of stuff? This is what they were stealing, methylamine. Okay, this is one of the ingredients that you need to make methamphetamine by the method that Walter White was using, okay? And so it was a primary amine. Most amines, I will tell you, smell horrible. They smell like rotten fish. In fact, putrescine, which is what you smell when you smell rotting flesh, is an amine. It's putrid, right? If you walk into a fish store and you smell a fishy smell, do not buy their fish, because it only happens when the fish start to rot. Fresh fish do not smell like dead fish, okay? And so don't eat the sushi if it smells. Words to live by. Amines, because they have that lone pair of electrons, they can react as both bases and nucleophiles. Remember my rule on nucleophiles? All nucleophiles are
Bases.
Lewis bases, but not all bases are nucleophiles. Here, an amine can be both. Okay? So I can take an amine. In this case, what kind of amine is that they've drawn up there? That is a tertiary amine. Yeah, so we take a tertiary amine, we're reacting it with some strong acid. In this case, let's just say A is chlorine, so HCl. I can make an ammonium salt. It's just an acid-base reaction. The base reacts with the acid and gives the salt. The salt is no longer an amine. It is an ammonium salt. Okay? Can I go backwards? Can I go from an ammonium salt to an amine? Yes, I can. All I've got to do is treat it with a strong base. So if I take the product and I put sodium hydroxide in there, it will go back to what we call the free base. Okay? When chemists talk about free base, we're not talking about doing drugs. The drug folks call it free basing because they know a little chemistry. Okay? But you can take an amine that has been protonated because it's reacted with acid, and you can treat it with sodium hydroxide and you can go back to the free base. Okay? But the amine can also function as a nucleophile. So it can react with some type of electrophile and give you a carbon electrophile bond. All right, excuse me, a nitrogen electrophile bond. So let's take our secondary amine here, and I want you to react it with iodomethane. Tell me what the product's going to be. What do you think the product's going to be? Help me draw the arrows in the mechanism. What's going to happen? Where do I start? I start at the lone pair. Yeah, I'm going to start at the lone pair. Right? So I'm going to start my arrow at the lone pair, and where am I going to draw it to? Am I going to go to the H? Am I going to go to the carbon? We'll go to carbon, right? What kind of reaction is that? What did I examine you on the last exam? This is a substitution reaction, but which one is it? Is it SN1 or is it SN2? It is SN2. It's one step, but it's SN2 because it depends on the concentration of this and this, right? So you've got the nucleophile attacking from the backside, the halogen leaving, and you end up with the ammonium salt in this case, okay? This is how we make so-called quaternary ammonium salts. You all depend on quaternary ammonium salts if you like to use things like antibacterial soaps. It turns out, for reasons I don't really know, but it turns out that a lot of quaternary ammonium salts will kill bacteria. They're good bactericides. They're relatively harmless to humans. Relatively. I mean, you wouldn't want to eat a bunch of quaternary ammonium salts. Okay, but I mean, putting it on your hands and stuff is usually okay. And they kill bacteria very, very quickly. And it's believed that what happens is it disrupts the cell membrane somehow. Okay? And so, quaternary ammonium salt. So if you like to use Dial antibacterial hand soap or something like that, if you'll read the back, you'll see something along the lines of cetyl trimethyl ammonium bromide or something like that. It's the active ingredient. I forget the exact name. But it is an ammonium salt that is used, and they make it doing this type of chemistry on an industrial scale, okay? Again, I hope what you're seeing is that sophomore level organic chemistry powers the world, okay? It really does. A lot of drugs are made by nothing more than a series of sophomore organic reactions. Antibacterial hand soap, big deal during COVID, right? It was made using sophomore level organic chemistry, okay? So, we do know that amines can react with acids, and they function as a base. This is nothing more than a Bronsted-Lowry acid-base reaction. What you'll find is that the pKa's of the conjugate acids are somewhere around 10 to 11. So the reaction goes from a stronger base and a stronger acid to a weaker acid, weaker base. So where is the equilibrium going to lie? Is it going to lie to the right or to the left? If I'm going from strong acid, strong base to weak acid, weak base, which one is favored, product or reactant? Product. Yeah, I heard somebody say that. Product. Remember, acid-base reactions always favor the weaker acid, weaker base. So I'm taking a relatively strong base, which is an amine. I'm taking a strong acid. In this case, it could be HCl. And I'm getting a much weaker acid, the conjugate acid, and a much weaker base. Okay? Chloride, if A was chlorine, chloride is not a very strong base. Okay? And so you can see that here. So if I take this amine, how would you name that amine, you think? What's the parent chain? It's an ethane parent chain. I heard somebody say ethyl. Yeah? So how would you go about naming it? If the functional group is an amine, how do you think you'd name it? Amino, okay. So how would you name it? Aminoethane. You just name it as aminoethane, okay? However, as we chemists typically like to make things more complicated than they need to be, nobody calls it that. We call it ethylamine. We use the amine functional group as the parent name and say that it's ethyl substituted. Okay, so you'll hear me call it ethylamine, right? Just like with the other one that we talked about from Breaking Bad, I told you it was methylamine. I didn't say it was aminomethane. So we typically name these as amine being the parent. What kind of amine do I have here in the second example? Is that a primary, secondary, or tertiary amine? That is a tertiary amine. It's got 3 R groups attached to it, right? 3 carbons attached to the nitrogen. It can react with weak acids even, like acetic acid, which is vinegar, and you can make these types of salts as well. So it will react with just about any acid and make an ammonium salt, right? So acetic acid, carboxylic acids, HCl, HBr, HI, all of those will work just fine, okay? And we can use this to our advantage. So, if I have a mixture of an amine and an alcohol, okay, I've got an amine and an alcohol, and I look at those, right? How many carbons do I have for each functional group? In both. Same number, yeah, which is what? How many are in this ring? 6. So I have 6 carbons and 1 OH. Is that going to be soluble in water or insoluble? It's going to be insoluble. It doesn't satisfy my 5 carbon rule, does it? Turns out that the 5 carbon rule also applies to amines. Okay? So that amine, do you think that that's going to be soluble or insoluble in water? What do you think, folks? Insoluble. It doesn't satisfy the 5 carbon rule. It's got too many carbons, right, for the amino group. So if I brought you into the lab and I said, I need you to separate that mixture, I want the amine in one flask and the alcohol in another, you'd be looking at me and going, well, what am I going to do? They're both insoluble in water. I can't pull one into water. Okay? But they're both soluble in organic solvents, right? So I could put it in something like dichloromethane. They both dissolve perfectly well there. But then what I can do is I can add just a dilute solution of hydrochloric acid, so 10% HCl. And water is less dense than methylene chloride, so it sits on the top. This is called, does anybody know what the name of that funnel is that you see in the ring stand? It's called a separatory funnel. Okay, and you can see that there are 2 layers in there, right? You can see the aqueous layer at the top. You can see the methylene chloride layer at the bottom. And what you do is you put a cork in the top and you rock the thing back and forth, kind of shake it up. You put it back in the ring stand and you let it separate. What do you think is going to happen? Well, the amine is going to react with the acid to make an ammonium salt. 10% HCl isn't really going to do anything to the alcohol. You might think, well, you might convert that to an alkyl halide, but not with 10%. Not without heating it up, okay? And so what do we know about salts? Are they more soluble or less soluble in water? Think about just traditional table salt. Is it more soluble or less soluble in water than something that's not a salt? Yeah, you can put a lot of salt in water, right? Why can you put a lot of salt in water? Because it's charged. What happens with my ammonium salt? It becomes charged, and now it will actually go into the water layer. The alcohol remains unreacted, and it goes into the dichloromethane layer. And the nice thing about this funnel is I simply drain off the methylene chloride layer. That removes my alcohol. That leaves the water around. So my amine is now an ammonium salt in the water. So now all I have to do is add base. That deprotonates it, makes it insoluble in water, and I extract it out. I pull it out doing that. So I can actually separate things using this acid-base chemistry quite effectively. Okay, this is a technique that we use all the time in the lab. So in my lab, we do make amines. And when we make them, we got to figure out how to get the amine away from all the crap that also got formed. And one of the things that we will do is put it in a separatory funnel, add some HCl, dilute HCl, shake it up, let it separate, take the water, put some sodium hydroxide in it, let it separate out again, and then collect the amine. Works very, very well, very, very easily. Okay, so we can use chemistry to do this kind of stuff. Okay? Not all of the amines have the same pKa. They're not all the same acidity or basicity, if you want to think about it that way. So if you look at ammonia, it has a pKa of 9.3. If you look at ethylamine, it has a pKa of 10.8. Okay? So what can you tell me as we add alkyl groups? What happens to the amine? Is it become more basic or less basic? More basic. Remember, the higher the pKa, the stronger the base, right? So what do you think will happen if I had diethylamine? Would it be a stronger base or a weaker base than ethylamine? Stronger. What about triethylamine? A little stronger, yeah. So the more alkyl groups you add to an amine, the more basic it makes it, okay? Very important concept there.
So does that mean that the less groups you have, the more acidic?
Yes, it goes exactly in the opposite direction too. Ammonia is more acidic than ethylamine. I wouldn't call either one of them an acid, but relatively speaking, that's true. Nitrogens on amines are sp3 hybridized. They have 3 groups that are singly bound and a lone pair, so that nitrogen is sp3 hybridized. They kind of look like a tetrahedron if you count the lone pair as a group. Okay? They have bond angles pretty close to what you would expect. It's about 108. Notice that the bond angle is a little less than what you would expect for a tetrahedron. Why is it a little less? In Chemistry 106, you learned about VSEPR. Does anybody remember VSEPR, valence shell electron pair repulsion? Right? I have an electron pair. It's going to repel those bonds, right? And so it tightens up the angle just a little bit. That's why it's not 109.5. It's a little tighter, okay? Now, if you take an amine and you put 3 different groups on it, it's technically chiral. A lone pair of electrons is different than R. R is different than R prime, and all of those are different than hydrogen. There are actually 4 different things around that nitrogen. A lone pair, R, R prime, and the hydrogen. So if you take this and make its mirror image, you will find that they are non-superimposable. So you would predict that amines are chiral. And in fact, they are by all technical terms. But you can't isolate one enantiomer over the other. If you tried to make one enantiomer, it would racemize and give you a mixture of both. Okay? It does some funny stuff. They have this funny ability. So see, the nitrogen, because it has a lone pair, it can change its hybridization pretty quickly. It can go from sp3 hybridized to sp2 hybridized. Kind of like an umbrella folding in the wind, right? And what happens if I made this, it would just invert and make that until it reaches an equilibrium. So this is called inversion. It happens on nitrogen atoms very easily. And what I just want you to know is that even no matter how hard you try to make just this enantiomer, you can't. So for all practical purposes, we consider the nitrogen with 4 different things around it, it's an amine anyway, as non-chiral, even though you would sit there and make your model and you would argue, well, this is not superimposable to that. Okay? And you're right. But it's because of this mechanism, okay, that allows them to be interconvertible. Okay? That is not true for ammonium salts. These salts are actually non-superimposable, and you can separate them because there is no lone pair of electrons to invert. It can't undergo a conversion from an sp3 hybridized nitrogen atom to an sp2 hybridized nitrogen atom. Just can't happen. Okay? So you can't ignore that. All right. A little bit on nomenclature. We've already talked a little bit about this. Primary amines can be named either using a systematic or common name. Okay? So, for example, the Breaking Bad molecule, the technical systematic name is methanamine. I don't like saying that. I call it methylamine. Okay? Cyclohexanamine. That sounds weird. It just doesn't roll off the tongue very well. I call it cyclohexylamine. Okay? So a lot of times we just call these as an alkyl substituted nitrogen. And we used to use the term amine. Okay? There are also aromatic amines. You all have already seen aniline. We saw that last chapter, right? So there's aniline. There's N-ethyl aniline. What does that name mean? N-ethyl amine. Or N-ethyl aniline. Why didn't it just say ethyl aniline? What does that N tell me? What does that big N tell me? Take a guess. Right now, if I told you to draw me ethyl aniline, where do you think some of you would draw the ethyl group? You might draw it on the ring, right? And some of you might draw it on the nitrogen. And both of you would have put an ethyl group on aniline. The N tells us what atom the ethyl group is on. So what does the N mean now? Nitrogen. On the nitrogen atom, I have an ethyl. That's what that means, right? Here I say O-bromoaniline. What does that mean? What is the O? Ortho. That's ortho-bromoaniline, right? So it's a substituted aniline. There are also different types of amines that can be aromatic. Pyridine is one of them. Pyridine is an aromatic molecule. There's also a lone pair of electrons on the nitrogen that aren't drawn, so it's an amine. Pyrrole is an amine. Piperidine is an amine. And pyrrolidine is an amine. You can have lots of different types of amines. They can be part of a ring. They can be part of an aromatic system. They can do all kinds of stuff. Okay? We've already talked a little bit about the 5-carbon rule, so we won't focus too much on that. What you'll notice is that amines have intermediate boiling points when you compare them to alcohols. They typically boil a little less than alcohols. Alcohols typically have higher boiling points, even though the molecular weight of these molecules is kind of the same. They both weigh around 73, 74. But you'll notice that the alcohol boils at 117 degrees. The boiling point of the amine is 78 degrees. Why do you think the amine boils at a lower temperature than the alcohol? It's because the alcohol has stronger hydrogen bonds. Alcohols form really strong hydrogen bonds. Amines can form hydrogen bonds, but they're not as strong because nitrogen is not as electronegative as oxygen. Okay, so that plays a big role there. Okay? You're going to find that all amines are soluble in organic solvents, regardless of how big they are, but the water solubility, again, is going to follow that 5-carbon rule. So if you have 5 carbons or fewer for every amino group, chances are it's going to be soluble in water. Okay? If it doesn't satisfy that, chances are it's going to be insoluble in water. So we can use that to our advantage. Okay. So there are a lot of amines that you come into contact with all the time that you may or may not know anything about. This time of the season, if you have hay fever and that kind of stuff, you're dealing with histamine. Okay, that is histamine. What kind of amine is this? This one, is that primary, secondary, or tertiary?
Primary.
It's a primary amine. But notice there's nitrogens also in an aromatic ring. Okay? So you start having allergy attacks, histamine gets formed that causes the physiological effects. What do you take to counteract that? Antihistamines. They are things that react with the receptors in your body to block out the histamine. So they react at the same receptor, but they don't trigger the physiological effect. Okay? And so it's kind of a cute way to play. But notice this antihistamine, okay, this so-called brompheniramine, don't worry about the name. What kind of amine is it? Primary, secondary, or tertiary? I got a secondary and I got a tertiary. Which one is it? How many hydrogens are on it? None, so it has to be tertiary, right? It's a tertiary amine. But notice it kind of looks like histamine. It's got an aromatic ring. This one's got some aromatic rings. And it's got an amine out here at the end of a chain, just like that one, except that's primary. This is tertiary. And so it can bind to the receptor, but because it's a tertiary amine, it doesn't elicit, for whatever reason, a physiological response. So the medicine keeps the histamine from binding and causing the, all the symptoms that you do. Notice this molecule, kind of complex looking. This is Tagamet. That's an anti-ulcer drug. So if you have trouble with ulcers, you might be taking Tagamet. You are taking a molecule that contains a lot of nitrogens that we would consider amines. Here's a couple of examples that you all may or may not partake in. So for those of you who need caffeine to get started in the morning, you're taking drugs. And that drug is caffeine. It is the most addictive drug in the world. More people are addicted to caffeine than any other drug. That's the molecule caffeine, okay? It's a bitter molecule. It's called an alkaloid. It's got a lot of nitrogen in it. Of course, we like this in our coffee or Coca-Cola. What other drinks do I guess Red Bull has a lot of caffeine. I don't know. So, you get hyped up on caffeine. Wake yourself up in the morning. Nicotine. Notice it has an amine in the ring, in the 5-membered ring there. What kind of amine is that? Primary, secondary, or tertiary? That is a tertiary amine, right? It's also chiral. Notice there's a chiral center right here, okay? Nicotine is, of course, synthesized. It's highly addictive. It's also highly toxic. The equivalent of 2 cigars contain enough nicotine to kill a human being if you were to ingest that tobacco. Swallow it. You can die. I mean, it's a very poisonous compound. It is manufactured by the plant to defend itself against insects. It's an insecticide. Okay, so when you're using your tobacco products, if you use tobacco products, it's poison, and it's an insecticide, and you are bringing that in, and so it can cause, it can act as a stimulant if you take low doses, but in large doses it does cause depression, nausea, and again, even death. There was a lot of work back in the early 2000s as the tobacco industry was changing. There's a lot of farmers that make their living growing tobacco. And so a lot of the tobacco industry was trying to find other alternative uses for the molecules in tobacco other than cigarettes and other tobacco products. And they focused an awful lot on nicotine. There's a lot of research that's been done on how can you use nicotine to make useful drugs, how can you use nicotine to make organic insecticides. And so there was a lot of work to try to figure out how we could keep the farmers growing their crop and making their money, because that's their livelihood, and have better ways to use the plant other than just to grind it up and smoke it, okay? Codeine, highly deadly. Okay, this is, in fact, I believe this is what Socrates drank, was a tea made out of hemlock. And it's the codeine that is actually the toxic agent. What kind of amine is that? Primary, secondary, or tertiary? That is a secondary amine, and it is also chiral. Notice it has a chiral carbon right here, 4 different things on that carbon atom. So very easily useful for a variety of things, but also quite toxic. So what's the take-home message for amines? They're toxic. What's the other take-home message? Is that it depends on the dose. You all have all kinds of amines running around in your body. Amino acids have amines. Okay? But a lot of these smaller amines, especially these secondary and tertiary amines, are quite toxic to we humans. Okay? So, kind of a problem. Here's a kind of interesting amine, dopamine. Okay? What do y'all know about dopamine? We think so, right? Yeah. Dopamine is typically considered a good mood kind of drug, right? It's actually released in our body. We make this very easy. What kind of amine is dopamine? It's a primary amine. It only has 1 carbon attached to it, right? It also has an aromatic ring that has what kind of groups on it? Hydroxys, which we called, when they're attached to an aromatic ring, they're called phenols. Yeah, so here's some phenols, there's some alkane in between, and there's an amino group, right? So we're bringing in all of these functional groups to make dopamine. So dopamine gets released, you have dopamine receptors, lots of things happen in the brain. And so they believe that this has implications in things like Parkinson's disease and things like that, that the dopamine receptors are having trouble. And so they've targeted this as a way to try to do a lot of things. I don't do anything in the brain, even think most of the time. So, you know, keep that in mind. So I'm talking just kind of off my head here, so to speak. But there's a lot of work being done, especially in the area of Parkinson's disease these days. All right, I'm going to call it there. We're going to pick back up with this on Tuesday. Remember that we will have our first workshop. You only have to attend one. Please only attend one. You will have to, Monday evening at 5:30 upstairs in 411. I will bring an exam. This is how this is going to work. I'm going to bring the exam. I'm going to project the exam. So nobody will actually have a copy. And I'll say, we're going to work problem one. You all will work on problem one. I'll give you about a minute or two to do that. And then I'll go to the board and have you all help me figure out what the answer is. Okay, so hopefully through that exercise, you all will figure out where your issues might be with a particular problem. We're going to go through all 26 problems. So please prepare to be there the whole time if you want your 60% of your missed credit back. And then we'll have the second one, if you can't attend on Monday, we will have the second one on Wednesday evening, again at 5:30 up in Tech 411.
So how long do we expect this to last? Like an hour?
It'll take probably more than an hour. Depends on how fast we go through it. Right? I can't predict. So, are we good with that? All right. Have a great weekend. Happy Easter. See you all next week. Enjoy your Good Friday off.